everyone. Welcome to the DI 101 webinar series. My name is Jared Evans, and I'm the Marketing Manager for Distribution International. This webinar series is an incredible resource offered to our customers, partners, and associates. By partnering with our manufacturers and our industry experts, we will deliver informative presentations about industry trends, new technology, new products, and product applications. We are extremely excited to partner with Johns Manville for today's webinar. Today's topic from our guests with JM will feature a two-pronged approach to corrosion under insulation. Let me introduce our presenters. We have Chad Meyer, who has been with Johns Manville since 2006. Chad is currently the Midwest and Northeast Regional Sales Manager for JM Industrial, a position that he has held since December of 2013. Prior to that, Chad was a Senior Account Manager with JM Performance Materials, covering various territories. Chad has a Bachelor of Science from Purdue University in Selling and Sales Management. We have Scott Sinclair, who is the Regional Technical Manager for the Eastern and Midwest US and Eastern Canada for Johns Manville Industrial. He has been in that role since joining JM in June of 2019. Prior to that, he was the Sales Manager for Scott Manufacturing and an insulation fabricator for OEM, HVAC, and appliance markets. From 2012 to 2015, he was the North America Sales and Technical Manager for ULVA Insulation Systems, a supplier of non-metallic insulation cladding solutions to combat corrosion under insulation in the oil and gas and petrochemical markets. Before joining ULVA, he was the Sales and Technical Manager for the industrial, marine, and petrochemical markets for Armacell, North America. He managed these markets for Armacell since joining the company as a Sales and Product Manager for the marine and offshore markets in 2005. Prior to that, he had more than 20 years of experience in various technical operations and sales and product management positions within the semiconductor and telecommunications industries. Scott has a Bachelor of Science in Electrical Engineering from Virginia Tech. We are proud to have them present today, and we certainly thank them for their time. We will respond to questions at the end of the webinar. To submit questions, please use the Questions tab on the GoToWebinar control panel. You can simply submit your questions at any point during the webinar, and we will answer the questions at that point at the end of the session. Without further delay, I will turn this over to Chad Meyer with Johns Manville.
Thank you. Scott, do you want to kick us off?
I sure will. Thank you, Chad. Thank you, Jared. And we'd like to thank all our guests for joining this webinar. Before we get started, we do need to do one little piece of housekeeping. Need to make sure everyone is aware that the information being provided in this webinar should not be used as a substitute for any professional engineering design or documentation requirements that are there by building code, contract, or applicable law, and that we recommend you please refer to any manufacturer's specific application guides, instructions, or guarantee requirements for any projects that you are designing. And with that covered, let's take a quick look at the information we'd like to try to cover with you today. Obviously, we're here to speak about corrosion under insulation, talk about what corrosion under insulation is, how it occurs, and what the impact of corrosion under insulation is to industrial facilities and the industrial economy. Take an overview of jacketing systems and the impact that a jacketing system can have in protecting against water infiltration. Also look quite a bit at the influence of insulation chemistry on corrosion under insulation, as well as the influence of hydrophobicity or water repellent properties in insulation. And then we will go over several different tests that have been conducted looking at the impact of different insulation materials on the rate of corrosion under insulation. So let's take a look at the impact of corrosion insulation to get things started. In 2013, NACE, or the National Association of Corrosion Engineers, conducted a study that they called the impact study and looked at the global cost of corrosion under insulation across all the different applicable market segments, and concluded that back in 2013, that impact was about $2.5 trillion. In addition to that, there have been several studies published in the U.S., mostly by owners and operators within the oil and gas and chemical markets, showing that 40 to 60% of the money that they spend in their annual maintenance budgets is actually spent addressing corrosion under insulation issues. So as you can see, the financial impact of corrosion under insulation is quite substantial and obviously should be at the forefront of a lot of people's focus when they're looking at insulation systems. Taking a slightly more detailed look at that information that was published in the NACE study, if you look at the numbers highlighted in red at the bottom row of the table where it says rest of the world, you can see the total cost of corrosion column shows that $2.5 trillion, and that represents a little more than 3% of the entire global gross domestic product. So again, demonstrating the significant financial impact. More relevant to most of us here in the U.S. or North America, you can see the block that's highlighted in yellow, looking specifically at the industrial sector within the United States, showing that the cost of corrosion in this sector was a little over $300 billion. And that is out of a total of about $450 billion for all of the U.S. market segments, so representing about 2/3 of that total in the U.S., or slightly less than about 3% of the U.S. gross domestic product. So again, showing that the financial impact of corrosion under insulation is very, very significant. That impact on the economy can occur as a result of several different factors or results of the corrosion under insulation. Fairly obviously, if you have corroded piping or equipment, you would be looking at the replacement cost of that equipment. In many instances where the owners or operators are concerned about the potential for corrosion, there can be over-design taken into account during the design phase of a facility to allow for the results of corrosion under insulation that will occur later. You obviously have, as we've talked about a moment ago, fairly significant maintenance costs as well as preventative maintenance costs involving things like inspection, painting, and repairs. If you do get to a point where the corrosion under insulation causes some type of equipment failure, then you have the shutdown of your processes as a result of that failure. There's always the risk of potential contamination of the product that is being produced if it is a failure that causes some type of a leak or a change in the production process. As well as losses of efficiency in the production or manufacturing processes. There can be product loss in terms of the capital equipment within the facility, equipment that's damaged and needs to be repaired, as well as possible product loss being the end product that is being produced at this facility. Of very high level importance is the risk to the safety and health of employees working in and around equipment that may be corroded and at risk of having a failure, as well as visual appearance of the facility, as is evidenced in this picture on the right-hand side of this slide. If you have customers of yours touring your facility and the facility looks like this, it doesn't present your organization very well. For corrosion under insulation to occur, you need a combination of conditions to exist as you can see in that little circular graphic image toward the center of this slide. Where you have the overlap of those conditions is what puts you in what they call the corrosion zone, or the opportunity for corrosion to occur. Those conditions include the presence of oxygen, water in the liquid form. Water vapor by itself will not initiate corrosion, but water vapor that makes it to a cold surface and condenses and then becomes liquid water can contribute to the opportunity for corrosion to occur. You need the presence of some type of a corrosive chemical compound. Typically, this would be some type of a corrosive salt introduced into the system from the environment or possibly from the insulation. You would need an acidic pH, something under 7, and then you need a temperature that is considered to be the corrosion zone for temperature, typically agreed by most folks in the industry to be 100 degrees to 350 degrees Fahrenheit. And we'll talk a little bit more about that shortly. When you're looking specifically at corrosion under insulation, the insulation material itself has unfortunately historically had a reputation of possibly causing corrosion under insulation, but the insulation material itself cannot actually cause corrosion. It's usually caused by the ingress of water, as we've discussed. However, the presence of insulation can promote corrosion by either retaining that moisture and or the contaminants that enter into the system from the environment, or possibly by the occurrence of electrolytes within the insulation material leaching to the pipe or equipment surface, and therefore increasing the corrosive nature at that interface. So as I said, there are concerns about the introduction of contaminants either from the environment or possibly from the insulation material itself. And those conditions can significantly impact the type of corrosion that occurs, as well as the rate at which that corrosion occurs. You can see some examples of fairly substantial events of corrosion in these pictures, as well as some damaged metal jacketing over the insulation, which is one of the prime conditions we see that allows water ingress to occur in the first place. So talking a little more specifically about what is corrosion. Corrosion is basically the deterioration of a metal. Metals in the form that we use them, so carbon steel, stainless steel, and other alloys of steel, are man-made materials derived from some type of an original metallic or rock material that's found in nature. Corrosion is an attempt by that material, it's a thermodynamic process by which that material is trying to return to its original rock material form. So there's a degradation of the material structure in an attempt to reduce its energy level back to that from which it originated.
There are several different types of corrosion that we see. A couple of those are on the screen here. You can have two dissimilar metals causing corrosion to each other. You can have salt water in direct contact to steel, which causes corrosion. Your materials over time in the environment can cause corrosion. We can have the salt water in the air. We see that corrosion on bridges and trusses. Simple steel, rust on steel corrosion. Something we're going to dive a little bit more into is this pitting or crevice corrosion that we see. So what is pitting corrosion? Pitting corrosion is a more localized form of corrosion. It occurs when one of the areas of the steel becomes anodic compared to the other regions. So what we can see on that graphic there is that red line pretty much represents the surface of the steel. We see that rust on the top. And then we see that area with the water, and then underneath it, that pit that forms. So that pit is that pitting corrosion. What happens is that pit extends down into the metal, and this is where we can see failures occur with actual minimal loss to the steel itself. So again, to review where we see corrosion happen, and what we see in this graphic here is a list of pretty much all of the insulation materials that are installed out in the market today on hot systems. The white area there is what we call our high-risk corrosion band, about 100 degrees up to 350 degrees. Now, corrosion can occur outside of those ranges, but if you're installing insulation in an application that runs in this temperature, we would consider that a high risk for corrosion potential. The other area we want to talk about is a little bit of a broader temperature range, and this is going to be below zero up to about 600 degrees. So we're going to call this the extreme risk category. And this is going to be for cyclical systems. So any system that is running both hot and cold, or simply a system that cycles hot and then at some point in time gets cycled down, turns off, and becomes ambient, or, depending on if you live in the Midwest, can go below zero just due to outside air temperature. But this is what we're going to call the extreme risk. So if you've got an application that's either a cyclical system or something, of course, that just gets cycled on and then cycled off, you want to make sure you're taking that into account because this is where you're really going to potentially see a lot of corrosion happen. What can we do to prevent corrosion? I would say that we can't fully prevent corrosion. All we can do is slow it down. So what we want to do is take a kind of a multi-step look in this. In step one, I want to focus on the jacket. So the first step in any well-insulated system is going to be that jacket. That jacket is going to be your first line of defense in preventing that water from intruding your system. You can see from the graphic here, these are some pictures of some well-maintained jacket systems. Second thing we want to look at is going to be the insulation design itself. You want to make sure that any clamshell pipe insulation is installed with all of your seams offset as much as possible. You want to make sure that it is also well adhered to the pipe with banding or steel wires. The other thing is when you install your jacketing system, want to make sure that the seam of the jacket is to the point where water is going to shed off that jacket. Also want to make sure that the jacket is installed with all of your overlapping joints, overlapping of course, and then you want to have silicone sealant applied in between all of those seams and joints. It's going to make the system watertight. And then we want to make sure we adhere to the pipe with stainless steel bands or clips. Now, all that being said, it is a jacket system, and we are human people, so sealants can fail, and we can make mistakes during installation. We want to make sure that we think of this as a weatherproofing system, not a bulletproof system. Good review. Step one is focused on the jacket system and the insulation design. Again, we want to make sure that system is sealed as much as possible. This is going to be your first line of defense for water intrusion into your system. And it all works well unless, like that picture on the right, it gets damaged. So what happens if it gets damaged? Well, we like to think of, again, that jacketing system as your first line of defense, but if it gets damaged and we view water infiltration as inevitable, you need to have a backup plan. So the backup plan consists of a few things. The first thing is you're going to want to make sure your pipes have a proper coating on them. Second thing is you want to make sure you have a maintenance system in place so that the jackets are being inspected, the insulation's being inspected, and of course your pipes are being inspected. Absent of that, you want to look at the insulation chemistry. So what is the insulation made of? And does the insulation provide anything that's going to help in that corrosion band where we potentially can see corrosion? Does the insulation contain a hydrophobic agent? Does the insulation contain an integral corrosion inhibitor such as XOX? All of these are good things to take into account when selecting the insulation you want to use.
All right, Chad, thanks for covering that aspect of the information. Let's take a look now at the insulation material itself and what Chad was just talking about in terms of looking at the properties of the insulation material and how it can help in combating the risk for corrosion under insulation. A lot of the insulation materials available today do have some type of a treatment to make them either hydrophobic or water repellent. The objective of this is to help prevent the opportunity for water to migrate into and through the insulation system should there be any type of failure in the jacketing system, as Chad was describing. There are several different insulation materials and types that do offer hydrophobic or water repellent features, and most are designed in a way such that they will still allow water vapor to pass through them if it does get into the system, but will not allow water in the liquid form to migrate through. This is a very important property to keep in mind in the situation where you may have a application where water vapor can migrate, or excuse me, you might get water into your insulation system, and at your given operating temperature, that water is going to boil off as steam. You want to make sure that that steam can pass back through the insulation and exit the system. Some examples of different insulation materials that do offer water repellent or hydrophobic properties include Johns Manville mineral wool 1200 pipe insulation. That does have an integral water repellent treatment. Johns Manville's Thermo 1200 calcium silicate is water repellent as well, designed to help give the contractors installing the material extra time to get it jacketed, even if there's a pop-up thunderstorm, without risk of the material getting damaged due to absorption of rain. Johns Manville's Insul-Thin HT microporous thin blanket insulation is treated with a hydrophobe so that it does have hydrophobic properties. And the Sproul 1200 expanded perlite material is also a hydrophobic material. In addition to these products, the Silica aerogel thin blanket insulation products are treated such that they are water repellent hydrophobic, and cellular glass insulation, which is typically considered to be a zero perm material, would therefore naturally be water repellent or hydrophobic as well. The one thing you have to be extremely cautious of and keep in the back of your mind when you're designing your insulation systems and selecting the materials is that most of these insulation products get their hydrophobic or water repellent properties by the addition of some type of a chemical treatment, usually some type of a silicon or an organic treatment. And most of those treatments oxidize away at temperatures between 300 and 600 degrees Fahrenheit. So if the insulation material sees those elevated temperatures for a long enough period of time, the hydrophobic or water repellent properties will oxidize away, and that will no longer be a feature that the material can offer. The other thing to keep in mind, kind of somewhat of a little bit of a saving grace in this, is that you will have a thermal gradient through the thickness of your insulation material. So while the inner layer of the insulation will see the process temperature at the pipe or equipment surface, and therefore potentially lose its water repellent properties, the outer thicknesses and the outer surface of the material will likely never see those elevated temperatures and therefore retain some degree of water repellent or hydrophobic properties. However, this can also be a risk in that if water gets into that insulation pipe interface, it will get absorbed into the material that has lost its water repellent property and then get trapped there because the outer portion of the insulation is still hydrophobic and won't allow the water to pass any further. So because in most instances these properties of hydrophobicity or water repellency are temporary, looking at the insulation chemistry itself is extremely important. You really need to look at a longer-term capability for providing protection against corrosion under insulation and minimizing the risk. And the insulation chemistry impact on corrosion is demonstrated through two different test methods that have been established. One is an ASTM test protocol, C1617, and the second is a newer long-term test protocol that's being developed by representatives from across the industrial sector. And what they are looking to do is try and develop a test method, test procedure that is more indicative of real-world conditions, but does it in a highly accelerated time frame such that they can look at the impact of corrosion in about a 6-month test cycle to be equivalent to what the material might see in a 15 to 20-year exposure in the real-world conditions. So let's take a look at the first two of these, and this is the ASTM test protocol C1617. This is a very detailed procedure for how you prepare and conduct the testing. If you look at the graphic on the right-hand side, you see a small metal coupon sitting on a hot plate, and on top of that coupon is a small piece of PVC pipe that is sealed to the surface of that coupon with a silicon sealant and O-ring, and then connected to the PVC pipe is a tube and a straw, which is used to introduce liquid into the test configuration. The sample preparation process includes weighing that metal coupon before you start the testing and preparing the solution that will be used to evaluate the impact of the insulation material on the corrosion rate. The insulation material is baked initially to drive off any residual moisture that might be in it. It's ground into a powder and then mixed with DI water, allowed to sit to give any contaminants within the insulation material an opportunity to leach into the solution. At that point, the solids remaining are separated from the liquid, from the solution, and then that liquid is dripped onto the surface of the coupon via the mechanism shown in the picture, and that is done for a period of 96 hours. The temperature of this is such that as the liquid drips onto the coupon, it very rapidly boils away, so replicating those real-world conditions of water getting into the insulation system but being evaporated off by high process temperatures, and then that process repeating over and over and over again. At the end of the 96 hours, the mass of the coupon is measured again, and then the initial mass and the final mass are compared, and a mass loss corrosion rate, or MLCR, is calculated for that individual material. This chart represents the results of testing performed by a third-party lab comparing the mass loss corrosion rate results for different insulation materials as compared to that of DI water. DI water is typically considered pretty inert, free of contaminants that might accelerate any type of corrosion, and so that is the baseline. The corrosion rates represented by the different colored bars on the chart are that ratio of the mass loss corrosion rate for the individual insulation material divided by the mass loss corrosion rate for DI water conducted as a benchmark or a baseline during each of these individual tests. As you can see by the orange, gray, and red bars in the chart, insulation materials such as mineral wool or silica aerogel have a corrosion rate ratio significantly higher than that of DI water, on the order of 2.5 to 3.5 times higher than the rate of the DI water samples. whereas the Johns Manville Insulthin, which is the microporous thin blanket material, has a corrosion rate very similar to that of DI water, as represented by a ratio very close to 1. And the Johns Manville Thermo 1200 calcium silicate and Sproul WR 1200 perlite products actually have a corrosion rate much better than that of the DI water baseline, shown by the ratio of less than 1. And that is the result of that active corrosion inhibitor that is included in both of those products. So to somewhat summarize what we just reviewed relative to the ASTM C1617 testing that's been done, you can see that insulation materials that do have some type of an active corrosion inhibitor in them do show a substantially reduced corrosion rate than either DI water or insulation materials that may not have a corrosion inhibitor but still offer some type of water repellent or hydrophobic properties.
So as Scott was saying, there's a secondary test or protocol that's been developed in the market, been developed by some leading industry professionals. And we subjected a couple of our materials to this testing. We ran actually 2 separate tests. So you can see on the left there, test 1 was run with the Insulthin HT and Silica aerogel blanket. And test 2 was run with the Sproul perlite, the Thermo 1200, and the Silica aerogel blanket. So this test is meant to try to sum up 15 to 20 years of what pipes would see in an environment close to a body of salt water. And we're trying to boil that down to about 6 months. And really, in essence, we're trying to take the pipe specimens to failure and then analyze what happened. You can see that this is a cyclical test. So we ran test 1 from ambient to 600 degrees. Test 2 was run from ambient to 900 degrees. What you can see with the graphics there, the graphic on the left is an overhead shot of the testing vat. What you'll see is the pipe insulated with the metal jacket. What you won't see is on the underside of that, there is a hole drilled in the metal jacket. The purpose of this hole is to allow water to infiltrate the system. Picture you're going to see there on the right are the same testing vats, this time full of liquid. So what we see on the chart just below that is the schedule. Again, we are alternating between filling and draining, ambient and process temperature. This is to basically go through as many wet and dry cycles as we can over that 6-month time. So for 2 of those 6 months, the vats were filled and drained with regular tap water. And for 4 of those months, it was a 1,500 part per million chloride solution. Again, a very corrosive solution, trying to look at what's going to happen when pipes are subjected to this punishing test. So we look at the results of the test 1. What you're seeing there on the left-hand side of your screen are pictures of the actual pipes from the test. So when the laboratory was done with this test, they took the pipes out of those vats, they cleaned the pipes, and then they analyzed it and provided the results. So the top pipe that you're seeing there is the Insulthin HT sample. The bottom pipe is going to be the Silica aerogel sample. What we're seeing on the table to the right there is going to be the maximum pitting depth in inches. And then what we're looking at here is how far those pits extended into the metal. So we reviewed from before when we talked about pits, that is where that highly localized form of corrosion that extends into your pipes. And what we can see on the Insulthin HT sample is that it was dramatically less than the Silica aerogel sample. When we look at the results of the second test, again, to review, we did the perlite, the calcium silicate, and the Silica aerogel, and we can see those pipes there on the left. We cycled this test between ambient and 900 degrees. And then we can see in the graphic there to the right, that table, we can see the results. We can see the perlite and the calcium silicate. Those pits extended about the same into the pipe samples. And then again, we can see that the pits extended further into the Silica aerogel sample. Now, when I present this data to corrosion engineers, they take a look at the pictures. They usually say, hey, that's great. But then when I show them this is really what they're interested in. So what we're seeing here is a close-up picture of the pipes, and it's basically a cross-section. So I'll explain what's happening. So the graphic to the left there, test 1 insulin HT sample. The black part at the top is actually just background noise. Then we can see the surface of the pipe. The red line indicates where the surface corrosion is. The white part at the bottom is the actual pipe itself. And then those little black areas where the blue line is pointing, those are the pits, that highly localized form of corrosion extending into the pipe itself. So we can look to the right there. This is the Silica aerogel specimen. Again, same thing, that black area to the top is going to be your background noise. The white area at the bottom is going to be the pipe itself. We can see the surface corrosion, and we can see that pit, that localized corrosion extending further into the pipe sample. When I show this to corrosion engineers, they've told me a few times that this right here is what they're concerned about. They're concerned with how far the pits extend into the metal, because this is where the potential for failure arises. Did we lose Scott there? So we want to understand the impact. You're back? All right.
Yeah, I'm back, Chad. Sorry about that, folks. Take a quick look, a little bit of a summary of the two different properties we've just been reviewing with you with regard to features that can be incorporated in insulation materials to protect against corrosion under insulation. You can see in the right-hand column, insulation materials that have hydrophobic or water repellent properties. Typically, this is something that is integral to the product, though in some cases it can also just be a topical or surface treatment. These treatments typically do oxidize off at temperatures between 300 600 degrees, as we discussed earlier. They are designed specifically just to prevent the ingress of water into and through the insulation system, and depending on the process operating temperatures, will not be present for the life of the insulation system. They will oxidize off and therefore not be there. Whereas the materials that are treated with an active corrosion inhibitor, like the XOX product offered by Johns Manville, this is, again, integral to the insulation material. It is not a topical treatment of any kind. It does not oxidize or burn off at elevated temperatures, up to and including the maximum operating temperature of 1200 degrees Fahrenheit for these materials. It is not designed to prevent water ingress. It's actually designed to be a safety net in the event that water ingress does occur, and it is something that is present for the life of the product. So let's take a little closer look at how these corrosion inhibitors work and how they can give the significantly better results as far as the test data that we've just reviewed, looking at different types of corrosion rates. The active corrosion inhibitor that is included in the chemistry of these materials is actually a combination of calcium, sodium, magnesium, aluminum, and potassium silicates that again are mixed throughout the construction of the insulation material as part of the manufacturing process. So when you have low pH or acidic corrosive ions introduced into the insulation and pipe system, either from the environment or from the environment, those high pH buffering silicates that are present in the corrosion inhibiting material will actually combine with those corrosive ions and neutralize them and bring it back to either a neutral or slightly alkaline pH, and therefore eliminate one of those conditions we discussed at the beginning was necessary for corrosion to occur, that being a corrosive or acidic environment. The second level of protection that these materials can offer is actually the development of a protective coating on the surface of the pipe. So in the event that you do get some type of failure of the insulation system, such that you do get water migrating through it to the pipe and insulation interface or equipment interface, what will happen is these silicate ions will be carried by the migrating water to the surface of the pipe. Those silicate ions will then create a silica gel protective coating on the surface. This isn't something that you would be able to see with the naked eye. It is at a molecular level thickness, but it is a protective coating. In addition to that, those silicate ions will combine with the iron compounds on the surface, metal surface, and form an inorganic iron silicate that will help to stabilize and strengthen that protective coating and provide that protective barrier against any future introduction of corrosives into the system. So if you take a review of what Chad and I have just gone over with you, you can see that a critical aspect of your corrosion under insulation prevention system or thought process, looking at insulation chemistry is much more important than that of just looking at having a hydrophobic or water repellent material. The results as far as measurable corrosion rates is significantly better, and it is also something that is there for the life of the installation. So in conclusion, as Chad described at the beginning, your first line of defense really needs to be a well-installed, well-sealed jacket system over your insulation material. Very, very important to take a look at the properties of the insulation material you're selecting. Having a hydrophobic or water repellent insulation material has its advantages, but it's not a cure-all, and that needs to be taken into account. They're not going to be permanent and can only prevent the migration of water through the material itself, not provide protection if you get leaks at seams or joints in the insulation material. And as we've reviewed, there are industry recognized test methods that demonstrate that the chemistry has a much greater impact than any type of hydrophobic or water repellent properties will. And we'd also like to offer to everyone participating today, we've gone over quite a bit of information in a relatively short period of time at a fairly fast rate. A lot of this information is available on Johns Manville's web portal called The Source. We have webinars on a lot of this corrosion under insulation testing, as well as data sheets on all of our insulation materials and other aspects of evaluating insulation products. And we would encourage you to go there and review some of this information to get much more detailed information than we had time to share with you today. And with all that in mind, we will open it up to questions.
Thank you, Scott. I really appreciate both you and Chad taking the time today. I think this was very informative. I don't have any questions that have been submitted up to this point. We'll give it a couple minutes, and just a reminder, if anybody does have questions, you can submit them through the little questions tab that you see in your GoToWebinar control panel. You can submit questions through there. In the meantime, I will say that for future, if you want to be sure you know about upcoming webinars, be sure you follow us on LinkedIn, or you can go to distributioninternational.com, and under the Resource Center, you'll see a page dedicated to this webinar series, and there's a link where you can actually sign up to get invites through that as well. We do have one question that just came through. Rebecca wants to know, is there a mineral wool board 2x4 that is treated with hydrophobic coating?
Chad, you might have a little better idea on this than I do.
Yeah, so for Johns Manville side, we do have one that we sell on the building insulation side of the business. On the industrial side of the business, I believe a few of the competitors to JM have a product. I believe we are in development of a product that I'm hoping that we will have out here sometime next year.
Thanks, guys. Let's see, we have a question from Adrian. For the online information, do we just go to the Johns Manville website?
So short answer, short answer, yes and no. Yeah, if you go to the JM website, if you go to just www.jm.com, you're going to see everything that JM has to offer. Usually what I tell customers from there is a link at the top that's going to say insulation systems. From there, usually I just navigate down to industrial, and then from there, there's going to be a link for the source. And then that's where you want to click on to find the source.
Great. No, and I will also point out that. Go ahead, Scott.
Another easy way to find it is if you just Google JM the source, it'll take you right to that page in the website.
There you go. And I will also say that today's webinar is being recorded and will be posted on the Distribution International YouTube channel. So if you go to YouTube and just search Distribution International, you should see a link to our channel, and you can see all of our videos, and this one will be posted in the next day or so. I believe that's all the questions that have been submitted. Again, I do just want to thank you guys from JM once again. Really appreciate this. Thanks to everybody who attended. Thank you to the DI associates who attended, and also certainly thank you to our valued customers that attended today as well. We really appreciate it, and we appreciate your engagement with these webinars. They continue to kind of grow and catch some momentum. So we'll be looking forward to more of them in the coming months. Thank you, everybody. Enjoy the rest of your week.
Hey, Jared, are we going to do that giveaway?
Thank you for catching me. Thank you. Okay. I do have a list of attendees. Chad, can you pick a number between 1 and 21?
19.
Okay, that'll be Jim. So Jim, I will reach out to you via email and make arrangements. Congratulations on winning the Pit Boss Vertical Smoker. So Jim, I'll reach out to you later this afternoon via email, and we'll make arrangements to get that to you. So thank you for reminding me. I would get emails about that if we did not do that. So thank you so much. Thank you, everybody. Enjoy the rest of your week.
Have a good week, everyone.